In this lesson, we're going to have a look at something called harmonic form. Now, harmonic form is basically a way of rewriting a sum of two different trig waves. So what I mean by that, if we've got a graph like this, if we just start with something like 3 sine x, okay? So this is a sine graph that's been stretched vertically by 3. And then if I have another wave, maybe something like 5 cos x, then I've just got these two waves here, the red one and the blue one, and I can add these together. Now, in real life, this happens a lot. Maybe if you study physics, you've done about the superposition of waves, which is where they add together. And in some places, they add together constructively, and in some places, they add together destructively. It also comes up a lot in things like signal processing, or anything that you're doing with signals and communications, and you've got various waves basically bouncing around a room and interacting with each other. So if I take these two waves and add them together, at some points they're going to add up, and at some points they're going to take away from one another. So for example, maybe at 0, if I just look at x equals 0, the red wave is 0 and the blue wave is at 5, so it's obviously going to be 5. At maybe let's say x equals 2, the red wave has got a value of about 3, the blue wave has got a value of -2, so that's going to make about 1. So I can just look at every single point and add them together. Now, luckily, Desmos could just do this for me. And this green wave is what we get when we add the two together. Okay, let's turn off the other two so we can see it a bit more clearly. So this equation here, 3 sine x plus 5 cos x. Now you might notice that it basically looks like a sine wave or a cos wave. It doesn't look too different really. And we can rewrite it as either a sine wave or as a cos wave, would be another way of describing it. So if I start off with, if we try and turn it into a sine graph of some sort, so if I start off with this purple one here, what I could do is I could stretch it. So at the moment it's obviously a bit too small. Maybe I need to stretch it by, well, it looks like almost 6. Maybe if we do 5.5 would be a good start. Okay, 5.8, yeah, something like that. We also need to translate it. So I'm going to put something in here. So I could move it left by a little bit. So maybe, I've got it in radians here, but I could do +1 to move it left by 1 radian, and that looks pretty good. Now, if I zoom in, I can see it's not quite exact, so I could try and work this out a bit more precisely. Maybe if I change these to some sliders, like this, and then I can play around with the values a bit more precisely. So if I increase R, I can try and be a bit more precise with that. And I can change A as well, and be a bit more exact with that. Okay, but basically I could rewrite it as some kind of sine wave, which has been stretched and then translated. I could do it instead as a cosine wave instead. So that purple line is a cos wave, and I'll just have to pick a different value of R and A to get it into the right position. Okay, now I could do this just by playing around with it until I get a good fit, but we should be able to do this mathematically as well. We should be able to rewrite 3 sine x plus 5 cos x as something in this format here, or with sine as well. And that's what this lesson is about. And this form here is called harmonic form, because it's to do with the harmonics of this function here and where they add together or subtract from one another. So let's have a go at this one algebraically. So 3 sine x plus 4 cos x is what we're going to try and plot. So we'll test this once we've calculated it. Okay, so this is the way that we're going to try and describe. And we're going to try and write it in the form r sine x plus something and r cos x minus something. So the way we do that is we're going to start by just equating the two together because they are the same. Okay. Now the right hand side of this equation I can expand using my addition formulae. So this is going to be sine x cos alpha plus sine alpha sorry, and this is r times this whole thing, sine alpha cos x. And it's still equal to 3 sine x plus 4 cos x. And now what we're going to do is we're going to compare coefficients of both sides. Okay, so compare coefficients. Okay. So if I look at my coefficients of sine x on both sides, so what am I multiplying sine x by? On the left-hand side, I'm multiplying sine x by 3. And on the right-hand side, I'm multiplying sine x, which is here, by r, and I'm also multiplying it by cos alpha. So I can say that 3 is the same as r cos alpha. I now do the same for cos x. So I'm multiplying cos x by 4 on the left. On the right, I'm multiplying cos x by sine alpha, and I'm also multiplying it by r. So I can say that 4 must be the same as r sine alpha. And now what I've got is essentially a pair of simultaneous equations. Okay, I've got two unknowns, but I've got two equations. 3 is r cos alpha, and 4 is r sine alpha, and I want to find out what r and alpha are. I think the easiest way of doing this is to actually draw a triangle to help you. A right angled triangle. So if this is r here, then, and this is angle alpha, then that would mean that this one here, which is opposite the angle, is r sine alpha, which we know is 4. This one here, the adjacent, would be r cos alpha, which we know is 3. And now using this diagram, I can solve to find r and to find alpha. So I can find r by just doing Pythagoras of the two sides. So that's going to be 5. And I can find alpha by doing inverse tan of opposite over adjacent. So that's going to be 4 over 3. And I could calculate what this is. And you can do this in either degrees or radians. It just depends what the question asks. Quite often it's in degrees. So we found r and we found alpha. So we can rewrite our equation 3 sine x plus 4 cos x as 5 sine x plus 53.1 degrees. So let's test our answer. So this is our function we're trying to plot, 3 sine x plus 4 cos x. And we think we can rewrite it as 5 sine x plus 53.1. There we go. You can see that when I overlay them, they're the same line. Okay, let's do part B. We're going to try and write it in cos. We're going to try and write it as r cos x minus beta. Okay, but we're still going to try and draw the same thing. So it was 3 sine x plus 4 cos x. So I'm going to expand, I'm going to swap the sides around actually, but we're going to expand this function using the addition formula. So it's going to be r times cos x cos beta. And that's a minus in the middle, so it's going to be a plus in between r's. Sine x sine beta. Compare coefficients. So if I look at the coefficients of sine x, 3 is the same as r times sine beta. If I do the coefficients of cos x, then 4 is going to be r cos beta. So you always end up with a pair of equations that looks a bit like this. And we can solve it. So this is r, this is angle beta. R sine beta, so sine, remember, is the opposite, is 3. And then r cos beta, the adjacent, is 4. And then I can use my right-angled triangle trigonometry again. So r still going to be Pythagoras, so it's 3 squared plus 4 squared square rooted, which is still 5, so that bit stays the same. But to find the angle beta, I can do inverse tan of opposite over adjacent, so that's going to be 3 over 4. So inverse tan of 3 over 4, which is 36.9 degrees. Okay, so we can rewrite this as 5 cos x minus 36.9. Again, let's change it. Let's test it on our thing here. So this is cos. Now I just need to change the number here. And we thought it was minus 36.9. Okay, and we can see it, they overlay pretty exactly. Obviously it depends on the accuracy of your decimal. If I zoom in enough, then they won't be quite overlapping, but this looks pretty good. For example, if I made it just 36 rather than 36.9, then that would be roughly right, but not exactly. Okay. Okay, let's have a go at another one. So this time we've got 2 cos theta plus 5 sine theta. We want to write it as r cos theta minus alpha. So I'm going to expand the right hand side. So this is going to be r times cos theta cos alpha plus sine theta sine alpha. Then we're going to compare coefficients. So my coefficients of cos theta, on the left it's 2, on the right it's r cos alpha. Now if I do the same as sine theta, the coefficient of sine theta on the left is 5, and on the right is r sine alpha. Now I can solve them. I can use this triangle. So that's alpha. And this is r, so r sine alpha, we know it's 5, and r cos alpha, we are told is 2. Now I can solve it. So r is going to be 5 squared plus 2 squared square rooted. So that's 25 plus 4, so root 29. And then to find alpha, we can do inverse tan of opposite over adjacent, which is 68.2 degrees. So my answer is root 29 cos theta minus 68.2. Now for part B it says hence solve this equation. Well, it says hence solve the equation 2 cos theta plus 5 sine theta equals 3. Well, that's exactly the same as the expression we had here. So what we're basically solving is root 29 cos theta minus 68.2 equals 3. That's the equation we've got to solve. And this is much nicer to solve than this one. Because this one here in green, this has got 2 different trig functions, which obviously makes it harder to solve. We can't do inverse cos and inverse sine at the same time. Whereas this one has only got 1 trig function involved, so we could definitely solve that. So if we proceed with solving this one, cos theta minus 68.2 is going to be 3 over root 29. Now once you reach this point, you might want to do a substitution like we did before, or you could try and solve it without doing a substitution, which I think is probably what I'm going to do here. So between 0 and 360. So what I'm going to do is find theta minus 68.2. So when I do inverse cos of 3 over root 29, the first answer I will get is 56.1. To find the next solution, I'm going to do 360 minus that, which is 303.9. Now normally I would stop there for between 0 and 360, but because I know that my next step is going to be to add on 68.2, it's worth finding some other solutions. So I could also have these two plus or minus 360. So if I subtract 360 from these, I get minus 56.1 and obviously minus 303.9. Okay, because they can also come from the fact that cos is symmetrical. Now I just need to add 68.2 to all my answers. And you can see that this negative 56.1 when I add 68.2 will then be within these limits. So if you're doing it not with a substitution, you do need to be slightly careful. But now I can just go through and find all of my answers. So I get 124.3. And the next one's 303.9 plus 68.2. That's going to be too big. So in fact, the only answers I'm going to get is going to be 124.3 and then minus 56.1 plus 68.2, which is just 12.1. Those are my answers there. So we can use this as well as just representing any equation which is written as something times sine plus something times cos. We can also use it as a way of solving those equations as well. Okay, here's another one to do. So we've got 12 cos theta plus 5 sine theta. We want to rewrite it as r cos theta minus alpha. So I'm going to expand the right hand side. This is going to be cos theta cos alpha plus sine theta sine alpha. Compare coefficients. So my coefficients of cos theta is going to be 12 on this side, and the other side is going to be r cos alpha. Coefficients of sine theta, 5 is going to equal r sine alpha. Then we can solve them. So the opposite is 5, which is r sine alpha. The adjacent, which is r cos alpha, that is 12. So we can find r by using Pythagoras. 25 plus 144 square rooted, so that's 13. And we can find alpha by inverse tan of opposite over adjacent, which is 22.6. So we can rewrite this as 13 cos theta minus 22.6 degrees. Now part B, find the maximum value of this function and the smallest positive value of theta at which it occurs. So this is the function that we've now got. And it's much easier to tell where the maximum is going to be from this function compared to the one above. Because 12 cos theta plus 5 sine theta, you know the maximum is not going to be 12 or 5. It could be a bit bigger than that, but how bigger? It's difficult to tell just from looking at that equation. Once you've got it in this format, this is just graph transformations of cos theta. So this is a graph of cos theta that's been stretched vertically by 13 and shifted right by 22.6. So by looking at this equation, the maximum, instead of being at 1, it is now at 13 because it's been vertically stretched by 13. So the maximum value is 13 and the minimum is obviously minus 13. Now where does it occur? Well, we want the maximum to be where this function is equal to 13. Well, that's the same as where cos is equal to 1. Okay, you could set it equal to 13 and then divide both sides by 13. But the important thing is this function is at its maximum when this bit, the cos part of it, is equal to 1, because that's the maximum value of cos. Now I've just got to solve this. So inverse cos of 1 is obviously going to be 0. And then we can add on 22.6. Okay. And hopefully that makes sense because we know that cosine is a maximum. Think about what the cosine graph looks like. It is a maximum at 0. So basically we want this angle in here to be 0. So to make that 0, theta needs to be 22.6. We could find the next point as well here. We could add on 360 to that because the whole graph repeats itself every 360. Okay. You should now be able to do exercise 7e, and this is also a technique that we'll come back to next lesson when we look at modelling real-life situations of trig as well. But you should now be able to do 7e. I'd recommend you do the questions marked with an E for exam.